What's up, everybody? Welcome to the 10th lecture of trig. Today we're really just going to be doing more of the same as what we did in the last lecture. Running through a bunch of different examples. To start off with, I thought we'd start with this particular problem here, where what we want to do is we want to use this particular substitution to rewrite this expression. So notice, when we say x is equal to 2 times tangent theta, what this implies is that tangent theta is equal to x over 2. Well, if that's the case, we know that tangent is equal to the opposite over the adjacent. So, because tangent theta is equal to x over 2, we know x must be the opposite side from our angle, and 2 must be the adjacent side. So why don't we just draw up a right angle triangle, pick one corner to be theta, and then represent this as a triangle. I've already done that here. We've got our nice right angle triangle. The angle theta is measured in this quarter, or in this corner. So the opposite side of it is going to be x. The adjacent side is going to be 2. And the hypotenuse, opposite of our right angle, is going to be x squared plus 2 squared, the square root of that quantity. Well, if you do that, notice we end up with the expression we want to rewrite using a trig function. Okay, so talked a little bit about what this looks like geometrically. Let's try to solve it now. The problem asks that we go ahead and just plug in 2 times tangent theta for x here. So let's do that. We got the square root of 4 plus 2 times tangent theta, that quantity squared. But we can go ahead and pass the square all the way through this, right? So we're going to end up with 2 squared times tangent squared. It's going to look something like this. 4 plus 2 squared tangent squared of theta. But we can simplify this a little bit. This is going to give us 4 plus 4 times tangent squared of theta. Well, looking at this, we can pull out that 4, can't we? We can factor it out of these 2 terms. When we do that, we're going to end up with the square root of 4 times 1 plus tangent squared of theta. So we've got the square root of 4 times the quantity 1 plus tangent squared of theta. Well, I do believe this is an identity, isn't it? When we go back to our identity sheet that I put on the front page of Blackboard for everyone, we'll find in the middle of it, under the Pythagorean theorems, or the Pythagorean identities, we have 3 different identities. It's the middle one we want to use here. 1 plus tangent squared of u is equal to secant squared of u. So we can replace this with the substitution, or rather with the identity, secant squared of theta. Well, we're taking the square root of all of this, so what we're going to end up with is 2 times secant squared of theta. Having said that, notice there is one catch to this. Is secant squared positive or negative? Well, to find out, we can look back at where we're bounded. We're bounded between 0 and pi over 2. So because of that, we know secant squared, my mistake, secant, not secant squared, secant. Made a mistake, typo. So it's 2 times secant of theta. But because of our bounds, we know we can just replace this to be positive. Leave the sign as it is. Cool. So let's move on. Let's look at some more problems. So this next problem is kind of similar to what we had done on the exam, right? I had asked you to use the identities we've learned previously to verify that these 2 statements were equivalent. But we're going to do the same thing here. To do that, we can start by looking at this fraction and saying, I can break this up, right? When we break it up, we're going to get secant squared theta over secant squared theta minus 1 over secant squared theta. Well, this is going to reduce to 1. And secant is 1 over cosine. So 1 over secant squared is going to be cosine squared. So what we've got now is 1 minus cosine squared theta. Well, this is one of our Pythagorean identities. It's just going to be sine squared. And we're done. That's all there is to it. Now I assume some of y'all might be looking at this, wondering how I went from secant squared, or 1 over secant squared theta, to cosine squared. The way I did that was by rewriting secant squared. I started with secant squared theta, and then I said, all right, well, secant squared theta is really just 1 over cosine squared theta. Which is really just 1 over 1 times the reciprocal so we get just cosine squared. So let's look at another example. Before we do, I just want to point out, this is largely what we're going to be doing today. Just reworking these identities and getting used to them. Trying to verify different identities using known identities. So in the same way that we used 1 minus cosine squared to get sine squared, we're going to do that same process, but in different types of combinations, different types of problems. Cool, let's move on. So again, we're just trying to verify the identity that's up here, right? Now, before we start this, a note on just general good practice. Generally, when we're trying to verify identities, it's best to work with the messier, more complicated side. So, for example, in this problem, we're going to work with these two fractions. And we're going to work through them to show that they are in fact equal to 2 times secant squared. Now to do that, what we're going to start off doing is multiplying both of them by 1. But to form this one, we're going to use the denominator of the opposite fraction. So let me show you what I mean. I'm going to sit here and we're going to say, all right, I know 1 over 1 minus sine alpha times 1 is still just going to be 1 minus sine alpha. But to form this one, to make this one, I'm going to use this denominator. So what does that look like? It looks a bit like this. 1 plus sine alpha over 1 plus sine alpha. And we're going to do the same trick to the other fraction. So we got 1 over 1 plus sine alpha times 1 minus sine alpha over 1 minus sine alpha. Now notice what we're going to get is these denominators are going to multiply together. So we're going to have the quantity 1 plus sine alpha times 1 minus sine alpha in the denominators. And in this numerator, we're going to be left with just 1 minus sine alpha. And in this numerator, we're going to be left with just 1 plus sine alpha. So writing that out, 1 minus sine alpha times 1 plus sine alpha with 1 plus sine alpha in the numerator. So that's this first fraction. And this second fraction, what we're going to have is 1 minus sine alpha all over the quantity 1 plus sine alpha times the quantity 1 minus sine alpha Now at this point, it might be a good idea to go ahead and try to reduce these denominators a little bit. So let's work them out. We've got 1 plus sine alpha, the quantity, times 1 minus sine alpha, the quantity. So we can FOIL this out. We're going to get 1. Let me write it slightly different. 1 plus sine alpha minus sine alpha plus, or my mistake, minus sine squared of alpha. Now notice these two terms are going to cancel, the plus sine alpha minus sine alpha. So what we're going to be left with is 1 minus sine alpha squared, right? Or well, sine squared of alpha. So we're going to use that to rewrite these denominators. Let's go ahead and do that now. So what we've got is 1 plus sine alpha over 1 minus sine squared alpha plus 1 minus sine alpha over 1 minus sine squared of alpha. Now we're going to bring these two fractions together. Since they share the same denominator, we can go ahead and do that, right? We can just add the numerators together, put them over that denominator. When we do that, we're going to have 1 plus sine alpha plus 1 minus sine alpha. This entire quantity over 1 minus sine squared of alpha. So what we're going to find is that these two signs cancel and these two ones add together. So we're going to be left with 2 over 1 minus sine squared of alpha. But 1 minus sine squared of alpha, that's cosine squared. So really what we've got is 2 over cosine squared of alpha. But 1 over cosine, well, that's secant. So really this is 2 times secant squared of alpha, which is what we were trying to prove. So notice, we didn't do anything really, right? We just massaged the algebra. We kept simplifying things until we got to the identity we were trying to prove. And that's more or less going to be the trend to these problems. Work with the more complicated side. If that takes you nowhere, then what you're going to want to do next is look for identities that you can apply. So, for example, we got to here, right? That looks like nowhere at first until we say, hey, wait, I've got an identity for this. 1 minus sine squared is cosine squared. And 1 over cosine is secant. And we were able to work it the rest of the way out. So again, this is going to be the trick. Work with the more complicated side, apply your identities. Just massage, massage, massage. There are going to be plenty of cases where you're going to get to a point and not know where to go next. That's to be expected. Probably means you need to go back and find an identity somewhere. But yeah, let's move on. Let's look at another problem. All right, so for this problem, your first impulse might be to try to FOIL this out, right? But isn't there an easier way of going about this? If we look, isn't this secant squared? And isn't this negative sine squared? Yeah, they are. They absolutely are. So using that, we've got secant squared of x times negative sine squared of x. Well, secant is 1 over cosine, so what we've really got is 1 over cosine squared of x times negative sine squared of x. Which we can rewrite as negative sine squared of x over cosine squared of x, which is the same thing as negative tangent squared of x. That's it. So just because it looks complicated doesn't mean the method that we're going to have to apply is complicated. Sometimes it's as simple as just saying, are those identities, yes or no? And then working from there. Notice it's actually pretty quick. Once we see these two are identities, we can just jump straight to here. But I wanted to show you all how to expand this secant out and verify it in a more methodical way. Let's look at the next problem. Now here's a decent example of when it might not be clear which route to go. They both sides look equally complicated, right? So in this case, why don't we instead start by breaking up the terms that we have. We know tangent is equal to sine over cosine, and we know cotangent is equal to cosine over sine. So let's start there. This is equal to sine x over cosine x plus cosine x over sine x Now, I'm going to skip a step here, but I'm going to tell you what it is I'm doing. We're going to multiply both of these fractions by 1, using that same trick from before, from earlier. So when we do, what we're going to end up with is sine squared x over cosine x times sine x plus cosine squared x over sine x times cosine x. Now we can pull all of this together under one fraction. And when we do that, we're going to get sine squared x plus cosine squared x over cosine x sine x well, sine squared plus cosine squared, that's just 1. So this is going to give us 1 over cosine x sine x. But we can break this up. Break it up into two different fractions being multiplied together. We're going to have 1 over cosine x times 1 over sine x. But isn't this secant? And isn't that cosecant? So what we have is secant x times cosecant x, which is exactly what we were trying to find. Cool, let's keep keeping on. So like the saying goes, rules are meant to be broken. And this idea of working with just one side is an example of a rule that's meant to be broken. For example, this particular example. What we're going to do is we're going to work with both sides and show that they reduce to something equivalent. Starting with the left side first, we've got cotangent squared theta over 1 plus what's supposed to be cosecant theta. Let me fix that really quick. Cosecant theta. Well, cotangent squared is equal to cosecant squared minus 1. And we can factor this apart into cosecant theta minus 1 times cosecant theta plus 1. So we started off with cotangent squared theta over 1 plus cosecant theta. Because cotangent squared is equal to cosecant squared minus 1, we know this first fraction is equal to cosecant squared theta minus 1 over 1 plus cosecant theta. We're able to factor out that numerator, break it apart. We're going to get cosecant theta minus 1, that quantity, times cosecant plus 1, that quantity, all of it divided by 1 plus cosecant theta. But these two terms are going to cancel. And all we're going to be left with is cosecant theta minus 1. All right, well, for now, let's let the left side rest. Let's now work instead on the right side. The right side is 1 minus sine theta over sine theta. Well, we can break that fraction up, right? We can break it up into 1 over sine theta minus sine theta over sine theta. Well, we know that that second term, it's 1. Let's go ahead and reduce it to 1. Well, what we're going to have then is sine theta minus 1. But sine theta, that's cosecant. So why don't we just go ahead and rewrite it? Cosecant minus 1. And notice both sides, left and right, reduce to the same thing. That's how we know that they're equivalent, because they reduce to the same thing. Now notice here, we haven't actually moved anything from the left to the right side or anything like that. We're not trying to solve for anything, nothing like that. We're really just reducing these things down using identities. We're saying, all right, we're given this. We want to massage it a little bit. Treat it like Play-Doh, mold it, fold it, do whatever you need until you get to a stopping point. Then if you need to, do it to the other side. And that's kind of the trend with all these problems. You're just going to massage the algebra. You're not moving one thing over to the other side and trying to solve. Don't do that. Here, you're just saying, what am I given? What do I have to work with? Can I get to a point where I can show both sides are equivalent? That's it. Having said that, that's all I've got for y'all today. If you have any questions, by all means, shoot me an email, come to office hours, whatever you have to do. Have a good one, everyone.